Alright, in this video we're going to talk about looking at residuals or plotting residuals to check model assumptions. Alright, and we're talking about the simple linear regression model right now. So just as a reminder, our simple linear regression model is yi equals beta naught plus beta 1 times xi plus the model error term epsilon sub I for I equals 1 to n, where n is your sample size. Right? And the assumptions for this model, the first assumption for this model is that the expected value of these error terms equals 0. All right. So how do we know if that if that's being held true? Right? That's what we're going to kind of talk about and show in this video. Right. Additionally, we have that the variances of these epsilon sub i's has to equal sigma squared, right? And notice sigma squared doesn't have a I on it, so it's the same variance for all these observations, right? And this is called the homogeneous variance assumption, right? And third, that we're going to talk about in this video, the third assumption is that these error terms are uncorrelated. So uncorrelated. And you know, there is another assumption that the error terms are normally distributed, but we're going to save that for another video. These first three assumptions, model assumptions, are necessary for us to have unbiased estimators B1 and B0, right? These are unbiased estimators of beta naught and beta 1. In order for these guys to be unbiased, these three assumptions are needed, right? Also, in order for the variance and the variance that we derived for each of these estimators, in order for that to be correct, we also need these three assumptions, right? In terms of, you know, constructing confidence intervals or doing tests or any additional inference of this model, you do need that normality assumption. Okay, so like I said, we'll talk about that in another video. But for right now, just in order to estimate unbiased, to have unbiased estimators of, you know, these model parameters, you need to start with having these first three assumptions. So these first three assumptions are very important to check. All right. So let's talk about the ideal case first. So ideally, right? If we were to plot y and x, right, in the ideal situation, so we have some random observations here, and they're linear. You know, there's a linear relationship here between x and y, and if I were to run a linear regression here, I would get like a line looks like this maybe, and maybe I missed a few. Okay, so you see how in this line, this is our estimated line, right? And if I were to plot the residuals, so remember, what are residuals? Residuals are estimates of that model error. So it's the lowercase e, right, which is not epsilon. This epsilon up here in the model, this is, you know, a model parameter, right? We don't know the value of these model errors, right? So we use e to estimate it. And e is the observed value minus the predicted value. Okay, so if we were to plot e versus x, right, we would expect it to be centered on 0. So here's 0, right? And see this first e, right? We see it's negative. It's pretty small. The second one is positive, and it's a little larger, right? This difference between the observed and the line, right? It's pretty small for the next one. The next one's super tiny, close to 0. And then this one is positive again, right? And negative, and tiny. So the next one's tiny. And we can continue like this, okay? So this difference between our line, or our observed value, and the line, right? These are our error terms, right? And so what we are seeing here, I'm just going to estimate the last few ones, but what we're seeing here is a random scattering, right? You're seeing these error terms just be randomly scattered around 0. All right, in this type of shape where you have a random scattering above and below 0, this is the ideal situation. Okay, that looks great. It looks like these 3 model assumptions, these assumptions here, are good to go. Okay, so what does it look like when things go wrong? Let's talk about that. So the first thing that could go wrong that I want to talk about is the model being misspecified. So the model is misspecified. Okay, and what do I mean by that? I mean, if I were to plot x and y, here's y, here's x, and this is the way the plot of x and y looks. Okay, so what we're seeing is a curve, right? And so the real model, right, the real model that we don't know about, it would potentially include a quadratic term, right, next to I squared, right? So then later when you go and you run your model thinking this is a linear relationship, right, and you run this model, right? Right, I'm going to put a star next to this error term because this error term is actually these last 2 pieces. Okay? And so this error term, right, you ran this green model, this model here. So this, but in reality the yellow model is correct. So the error term is going to include this quadratic this quadratic term here. Right? And so then when you take the expected value of your error term, you get beta to x sub I squared. You get that quadratic term plus the expected value of the error, the model error, which is 0, right? So that's 0. So basically that goes away, right? And so then you see, okay, this is the model assumption that's being violated here. My expected value is not equal to 0. Right, which is that first model assumption. So when you have a misspecified model, right, you're going to be basically violating this first model assumption up top here. Okay, so what is it going to look like? Well, when you run your regression line, your regression is going to do its best job fitting, a linear line is going to do its best job fitting those data. And when you plot your error, right, or your residuals versus x, okay, let's go. See, we have negative, positive, positive, positive. So let's see, I'm going to start it at 0. And so this first one is negative, then it's positive, and it's really close to 0, right? This is 0 here. Then the next one is negative, then the next one is positive, positive really close to 0, positive larger, positive, positive, positive really close to 0, positive, and then negative really close to 0, negative, negative, negative residual, negative residual, and negative residual. So it looks something like this, right? So what you're seeing here, what is this shape, right? It's looking like this. Your residuals are following this shape. Okay, so whenever you see a kind of a trend like this, right, you can start thinking, oh, maybe my model is misspecified, right? And you have to think of ways to correct that. You might use a different model. You might consider a transformation of x, right? There's lots of ways you can think about solving this problem, but certainly when you're seeing this relationship, you see how ideally you should have random scattering around 0, but now you're seeing this relationship between the error terms and x. Now you're thinking, okay, maybe my model is misspecified. Okay. Another thing that can go wrong is we can have a violation in the homogeneous variance assumption. All right, so what would that look like? Okay, when you plot x and y, you'll see some sort of strong linear relationship between x and y maybe towards the beginning, and then the relationship kind of gets a little wider out. Okay, something along looks a little bit like this. This is, and then so when you run your regression, right, do your best job fitting, and you have your fitted line here. And then when you plot your residuals is centered on 0, you'll see, so here's x. So what you see is we have some random scattering of residuals really close to 0. These are small residuals, and then the residuals get much larger. Okay, you see these lines, these little red lines, they start out small and random, close to 0, and then they get larger. Okay, and so you end up with a shape kind of like this, right? And so a cone shaped of the residual, right? And it doesn't necessarily have to be this way. It could have been the other way, right? Like you could have residuals that are really small when x is large, and then are really big when x is small, right? So it could have gone the other direction. Okay, but the point is, once again, you're not seeing this nice flat line around 0, right? So when you see this type of shape for your residuals, when you plot the residuals against x, then you're thinking, okay, this is a violation. The variability is really small when x is small, and then it gets much larger when x gets larger. So this is a violation of the homogeneous variance assumption. So the error terms do not appear to always be sigma squared. Rather, there appears to be a relationship for I, right? Okay. Thirdly, in this video, we want to talk about the error terms being correlated. All right. So if your error terms are correlated, how can you tell? Most often, or not most often, but very commonly, error terms are correlated due to some sort of time trend that is not being considered in the simple linear regression model. Okay, so you'll often see people, they'll, instead of plotting the residuals versus x, which is what we have been doing, they'll plot the residuals versus order, right? The order that you observed your data. Now, note that this is only going to be appropriate when you know the order that your data were collected. If you don't know the order that your data is collected, then you can't do this, unfortunately, right? And of course, this is going to tell us if there's some sort of correlation when it comes to time. Now, you can have correlation due to other factors, okay? But like I said, this is a very common problem that people need to consider the potential for a time trend, okay? And if you need to consider the potential for a different reason for the correlation, or different potential correlation, then you would do the exact same thing, except instead of using time, you would do residual versus whatever that other thing is that you think that potentially could be causing a problem with your residuals being correlated. Okay, so let's start with, once again, our ideal case. What is ideal? So ideally, when you plot the observation order, okay, versus E, right, it'll be centered on 0 and just like a random scattering, okay? So it looks very similar to our original ideal type plot, right? So once again, you kind of have this random scattering here tubed around. So that's the same as basically our ideal up here, except now instead of it being X, it's the order observation. Okay, so this is ideal. Now, when there's a time trend, a very clear time trend, what you'll see is when you do the observation order versus E, your residuals, what you'll see is basically a trend, right? It may look like a linear trend, right? Okay, and if you see a time trend like that, you need to consider, instead of using a simple linear regression model, you're going to need to consider there are models that are appropriate for time series. Okay, so there's a very clear time trend if you were to see something like this. Another thing that you can see is a positive serial correlation. Right, and if you have a positive serial correlation, here's 0, and these are your residuals versus the observation order. Okay, what you'll see is something like this, where this is a positive residual, and it's large, and the next one will also be positive and large. The next one's also positive and large, and they're kind of similar to each other, right? So if I go negative, I'm negative and small, negative and small, negative and small. So I have some sort of relationship, right, where one is similar to the next, which is similar to the next, which is similar to the next, which is similar to the next, similar to the next, something like that. Okay, that is a positive serial correlation. Okay, and you could have a negative serial correlation. A negative serial correlation. All right, so this is your observation order and your residuals. And if you have a negative serial correlation, you'll see, so if I have a large positive correlation, then the next one will be large and negative, right? And if the next one is small and positive, then the next one will be negative and small. If the next one is large and negative, the next one will be positive and large and positive. So what you're seeing is basically the opposite is always happening. So we go from large to large positive to large negative, small positive to small negative, large negative to small or to large positive, right? So the sign changes, but the magnitude is the same, right? So if this one is small and positive, then the next one will be small and negative, right? If the next one is large and positive, then the last one will be large and negative. Okay, so that's what a negative serial correlation looks like. And if you see any of these, right, since it's being plotted by observation order or time, if you see any of these type of things, then you need to consider using a different model, a model that that's for time series.